Okay, ladies and gentlemen, the conference will begin shortly. Please have a nice seat and make sure to mute your microphone. And I would like to remind you to rename your name with the following format: Zoom room, paper ID, name. Example 2154 Nanasari. And I will repeat, please change your name to the following format: Zoom room, paper ID, name. Example 2154 Nanasari. Okay, good morning, ladies and gentlemen. A very warm greetings to each and every one of you. I am Haya Alfinesa as your master ceremony for today's conference. Welcome back to the second day of the 11th International Conference on Physics and its Application, ICOPIA 2022. And also, welcome to the Honorable our keynote speakers, Mr. Acep Purkon, PhD, from Institut Teknologi Bandung, Indonesia, Professor Dr. Nafarizal Nayan, from University Tun Hussein On, Malaysia, Letkol Laut Pelaut Dr. Dian Adrianto, MSI, from Indonesian Navy Hydro-Oceanographic Center, and Dr. Andes Iwan Yahya, MSI, from Universitas 11 Maret, Indonesia. And also, we are welcoming to all presenters and participants for the second day of ICOPIA 2022. Next on agenda, we will have a photo session. Please to our honorable speakers and all of our participants to turn on your camera. Please prepare. Okay, slide 1. Let's take a photo. 1, 2, 3. Thank you. Slide 2. 1, 2, 3. And last but not least, slide 3. 1, 2, 3. Okay, that's enough. Thank you. Excellencies, ladies and gentlemen, we will begin the first session of today's plenary lecture that will be led by our moderator, Professor Budi Purnama, a professor from Physics Department, Universitas 11 Maret, to carry this session. But before, let me check you, Mr. Budi. Could you hear me?
Yes, I heard you.
Okay. Hello, Mr. Budi.
Halo, Assalamualaikum.
Okay,
Aya.
Waalaikumsalam. Okay, thank you, Mr. Budi. Then please welcome Professor Budi Purnama.
Okay, thank you. MC have invited me in here. Okay, thank you very much for ladies and gentlemen. Today, I would like to modern the two scholar when he is join us when we are here. The first is Acep Purkon PhD from Kelompok Lahan Fisika Bumi dan Sistem Kompleks ITB. Good morning, Mr. Acep.
Yeah, good morning.
How are you?
Good.
Okay, thank you for your joining with us here. And the second one is Professor Dr. Nafarizal Nayan from University Tun Hussein On, Malaysia. Assalamualaikum, Professor.
Waalaikumsalam.
Thank you for joining with us here. How are you?
I'm good, thank you.
Okay, thank you very much. Before the two scholars deliver his talk, I would to introduce for the first is Mr. Acep Purkon. He is graduate from Institut Teknologi Bandung for undergraduate bachelor program and also master degree from Institut Teknologi Bandung. And he is graduate from doctoral degree from Kanazawa University, Japan. And he is expertise in some field from especially and system complex. Yeah. And today he will deliver regarding the density function. And the second one, Professor Dr. Nafarizal Binazan, he get the bachelor engineering from electrical and electronic engineering and information engineering Nagoya University. And he get the master engineering, also doctor engineering from electrical engineering and computer science, especially plasma nanotechnology research center Nagoya University. The Professor Nafarizal work experience in head of microelectric fabrication laboratory, Faculty of Electrical and Electronic Engineering UTHM, and also head of microelectronic and nanotechnology Samsudin Research Center UTHM. He also joined some professional affiliation such as IEEE, and also have social work experience. And he has also have more than document academic paper, over than 200 paper, and he get more than 1,000 total stations. Okay. Today, two scholars will deliver the expertise, and the first chance I will deliver by Dr. Acep Furqan. This time for use, the time for deliver time is 40 minutes. Okay.
Okay, thank you very much. Good morning, everyone. So, of course, this is a great honor for me to deliver talk in this event, the 11th International Conference on Physics and its Application. I think it's a long story about this conference. So it's great honor for me to deliver or sharing some information about some work here. Thank you very much for the chairman, Professor Budi. And yeah, I'd like to talk about the effect of co-doping rare earth molecules in gallium nitride on electric and magnetic properties using density functional theory for applied nanosensor and energy saving. So I'm from physics department, Institute of Technology Bandung, and here some collaborator, Pak Yusuf, Afla, Dinan, and Saito from Kanazawa University. So, yeah, this is my affiliation here, and this is my group for a complex system study, past member and current member as well, and some application for some interdisciplinary physics or green physics or something like that. And also some topic related to some interdisciplinary physics. Okay, I'd like to start from the background. As we know, the energy crisis, it could become from overconsumption of energy, and to reduce this the consumption, maybe there are many options, and many researchers try to solve this problem as well. One of the candidates is to make devices more energy efficient, such as LED. And gallium nitride is the important key material for completing the invention of white LED. So if we see our world at night from the top or from the atmosphere, so many light pollution, something like that. And as we know, from 2014, the Nobel in Physics for blue LED, and then we can see from our perspective, from Indonesia itself, to investigate or to grow some best candidate to support for LED, for example, coming from the rare earth. Of course, this is a warm discussion about this topic. In Indonesia itself, rare earths, there are plenty of this one, and we can see the distribution as well. And as we know, the rare earth is high-tech material, high technology material for some product, and so many high technology product coming from this one as well. So I think this is our this is good news for Indonesian itself to study about this one, because plenty of material we can investigate. And we can see some situation, the replacement of LED and filament, something like that. So it can reduce some problem itself. We can make some comparison for the efficiency and for the application. And we can see as well from semiconductor, it's possible for LED, and for gallium nitride as well. We can get 3.5 electron volt. And interesting one, if we make some dopant using rare earth, something like that. From this, sorry, this is in Indonesian language. But I can show some information here with some co-doping candidates. We can select, we can make a good color with some composition. So actually, there are some. We can be like safe in food. We can select the best one we want, and we can check the candidate using this proportional or proportion for this contribution. This is the situation, and we can see by combination RGB, red, blue, and green, we can make more candidate for this one. How about rare earth in gallium nitride? So rare earth itself, they have a electron configuration like this one. And when we check rare earth in this periodic table, we can see this situation. And for the, I think it's okay. So by using this one, of course, there are more application with low energy consumption. So the red and green light itself discovery first. but for blue light is needed to achieve the full color spectrum and white light. And gallium nitride is a direct wide bandgap semiconductor, using this one. And gallium nitride successfully being used for bright blue LED. So you can see the direct bandgap and indirect bandgap. Direct bandgap is more light, indirect bandgap is less light, something like that. Of course, everyone can make some imagination or some idea about this one. Yeah, as comparison, this LED time by time, you can see the progress and grow fast about this application. For some background theory, we can see light is inactive semiconductor layer. Yeah, I think this is a basic information for the process, and for this physics forum, I think everybody know this one. This is just some discussion and idea about this. And this is how the process to create, yeah, the light, something. I skip this one. And to make white color, of course, we need some color mixing, partial color conversion, or complete color conversion. Using this one, we can make a modification, modifying active layer by doping. When the candidate is rare earth, with the complicated configuration or something like that. But I think this is very challenging to see, and we have some potential good candidate for this one. So in wide bandgap, direct wide bandgap, yeah, in gallium nitride semiconductor producing blue LED, energy gap like this one, yeah, for direct bandgap and indirect bandgap. I think some theory we can find in solid state physics. And interestingly, in rare earth element, yeah, you can see some mix or some calculation about this co-doping, especially for the proportional. How about the future rare earth element? Yeah. You can see and economically having potentially creating new material development, yeah, in optoelectronic, in neomagnet and metallurgy. Something like that. But how about the current situation? Who produce rare earth? The biggest producer is China. This is the old information, 2005. More than 50% world market share. So I mean the high technology materials coming from this country. Yeah. How about Indonesia? And Indonesia mainly Bangka Island, Belitung, Singkep, and Riran, Kalimantan. I think, and this country should be taking a lead, yeah, about this material, because plenty of material exists here. And how about the other reported rare earth with gallium nitride potentially applied in optoelectronic devices, yeah, solid state lamp, flat panel display, laser, fiber optic, and something like that. Dope rare earth to gallium nitride decrease the temperature. This is very interesting properties, yeah. Thermal quenching better than semiconductor. Particularly rare earth gallium nitride using EUER enabled to emit red, green, and blue, And rare earth interaction as dopant gallium nitride is interestingly to study illumination process. I think it's open to many subjects to be discussed. And how about the technique we use? I think everyone here is familiar with the DFT, density functional theory, 1998 novel in chemistry, Walter Kohn and Pupel. I think for long wait work, yeah, I think to 20 years or something like that. Yeah. Finally, deserve to get this one, yeah, because it opened many analysis using this very success model, success technique to investigate some properties. For the theory, I think everyone can find yeah, and be found in some the textbook about this technique, find some equation, something like that. I can skip this one, but basically it's very smart idea to use this one, and we can get the exchange correlation coming from LTA or GGA. But of course, now so yeah, growing fast to investigate more detail case by case case study based on the situation. So many idea to yeah, to be discussed about some good potential in some cases, and more complex interaction. So I think need more the best explanation for the best candidate for the potential, and it's make everyone to propose, yeah, freely the best one, as long as it can be explained by some experimental result. Okay, our model start from this Wurtzite supercell 32 or 72 atoms, using this kind of supercell. I'm not, I don't know somebody familiar with this. If there are some familiar, maybe I can skip this one. But this is the situation. And then for the supercell 72, gallium 32, gallium 15, and nitride 16, and X can be filled by several candidates from rare earth, yeah, PR, ND, AU, TB, TY, and ER. So we can make some general, we can see some general properties about this one, some interesting properties about this one. And for the supercell 72, yeah, of course, I mean, gallium 16 and nitride 16, yeah, but we replace one gallium with rare earth atom, and 72 the similar way, 36 gallium and 36 nitride, and one gallium we remove and replace with one atom. This is from the beginning, just to check our calculation is correct or not using this one. And then after we can make validation, we can go to the next one. Here we use exchange correlation to analyze gradient approximation with pseudo potential ultrasonic and so on. So this is some parameter to make this one. And step as this is a common step, yeah, geometrical optimization, unit cell, total energy calculation, and so on and so on. Yeah. We use program case, yeah, developed by some consortium in Japan, including this collaborator from Kanazawa University, also developed this software. Okay. For example, we can check. This is another story before. I mean, just to validate our calculation is correct or not. For example, when we calculate the other materials, we get the best result. Yeah? And using similar way, yeah, we can see the other problem. Yeah. Yeah. So, okay, this is another. Nah, this one. The idea would side like this one, the structure, yeah. And our calculation, yeah, using this optimization, our calculation, we can get this one, yeah, in the center with parameter A, like this one, we get a calculation like this, yeah, in this work. I mean, in this work and this other calculation, another people calculate like this one. This is just to validate this calculation is correct or not before we continue to the others. So using this and the experiment also, we can, yeah, it is a good agreement with the experiment. It means we can continue to the other calculation. And then this is another story. I skipped this one. This is some our calculation and comparison stability. I mean, the similar way we can use to calculate this one. Okay, the geometrical optimization of unit cell is very important before we move to the other calculation. And this we can, yeah, can see like this, and then geometrical optimization of unit cell using cutoff, yeah, like this one. I think this is just to validate. Okay, this is interesting one. After calculation, yeah, the calculating bond length nitrate, okay, for this supercell like this one. This is our calculation, and this is another calculation, another people, and this is experiment. Yeah. Not all experiment provide, yeah. But we can see it's good enough to validate about the calculation, and very interesting because yeah, we can move to the other one. Yeah. And this band structure like this one with energy level like this one, yeah, with doping and without doping, and band structure like this one as well for supercell using 72. And this is the other ones for a band structure like this one. We can see some interesting thing, yeah. And the other rare earth, yeah, with AU and ER and like this one. Yeah. Now, try to make a composition. Yeah. Another composition, for example, using ER, for example, 1.3%. It means actually a supercell with 72 atoms with one one doping. Yeah. How about if we add the composition of doping? Yeah. For example, 3.1. Yeah. ER2. It means the composition like this one, and more sign this one. And we want to see about the properties, yeah? Like this one. Okay, and start from a supercell like this one for pure gallium nitride, the total energy like this one, and for one atoms doping in 72, the calculation like this one, more and more and more and more. This one, like this, like this, like this. So we can summary about this calculation. For example, for 0%, it means only gallium nitride, the total energy like this one, and for the other composition, it means some proportion of the doping. Okay, it's a some interesting result, yeah, like this one, and we can estimate actually the wavelength, yeah, using this simple theory. For example, we can estimate using this composition, we can expect the blue color, yeah, using this one. So before we can go to the experiment, actually we can expect, yeah, theoretically what kind of color we can produce using this composition of the doping. How about to put the doping? It's another story, yeah. But I think the composition is very interesting. And for example, like this one, yeah, it also some explanation about this one. And about this one, okay, and then this one. Based on the periodic table, we can see some interesting one, yeah, about the calculation. And yeah, for wavelength, we can estimate what kind of color they can produce based on this one. Something like this. And this is our prediction, yeah, based on the calculation. So we can expect, yeah, based on the energy and wavelength. Yeah. So I think this is a visible light. We can expect PR like this color, ND like this color, and SM, AU, GD, AR, and TM. The color looks like this one. And try to modify by adding some dopant, what kind color. Yeah, of course, this is very gradation color, so we can make very combination about the color. And then this is another interesting one. Yeah, of course, there are more yeah, need more explanation, need more theoretical explanation about this one. Is very interesting because the atom in rare earth itself, it's very interesting. Yeah. Okay, we can see like this, especially the orbital. This one is very theoretically is very interesting to be explored. The same, yeah. The symbol of presented valence band energy like this one, yeah, and different conduction like this one, yeah. I think if someone have interest about this one, it's very interesting. The reason, yeah, how or the process, of this one. Okay, I think I can skip for this one. Sorry. This one. Yeah, we can add not one type of dopant, but also we can add more different dopant. It's also interesting, yeah, more interesting for someone who want to check, yeah. For example, how about ER and TM, for example, yeah, like this one, and then we can check not individual or not one type of dopant, but we can make some combination. Yeah, like this one. Sorry. Okay. And then we move to this one. Yeah. We can see for individual dope, yeah, TM, AU, and ER, we can get this one, and the color is like this one. TM can produce blue color, ER can produce green, and AU can produce red or something. How about combination? We want to find another color. I think this is theoretically like this one, yeah. ER, TM like this one, and we can get this energy band gap. So it's mean 588 nanometer. It's mean yes, some kind red, yellow, something like that. In experiment, concentration less than 2%, yeah, 0.4 electron below conduction. I think that's all my talk. Thank you very much.
Okay, thank you very much for your inspiring talk, Mr. Acep Furqan. Maybe for the attendance, please keep your question to Mr. Acep Furqan and we shift to second presenter. I will ask Professor Navarizal bin Najam to the second presenter. This time for yours.
Okay. Can you listen to me? Is my voice clear?
Yes, clear.
Okay, all right. So I share this screen. Okay. So first of all, thank you very much from Budi, and thank you ICOPIA Secretary for inviting me to give this talk. My name is Nafa. So full name is Nafa Rizal Nayan. So call me Nafa, please. And I'm from University Tun Hussein of Malaysia. You can see at the top here. Sorry. So from the University Tun Hussein of Malaysia here. All right. So then, and the title of my talk is going to be this plasma processing and diagnostic. And I belong to this microelectronic and nanotechnology Samsudin Research Center. So one of the center that we have and at the university, we have 5 center of excellence actually. And one of it is on this micro and nanotechnology. And we are under the umbrella of this institute. We call the Institute for Integrated Engineering. And I'm also as a member of IEEE Society. And we joined, I'm the executive committee for this ICOPIA Nano and Sensor Council, Malaysia Joint Chapter, and also for the Electron Device Society. And we also have this Malaysia Nanotechnology Association, where here we gather all the people that work on the nanotechnology. So we create this association to engage each of the activity that we have. And I'm also a founder of this Nagoya University Alumni Association for Malaysia branch. So we have this one. So I was studied in Nagoya, Japan, since 1999 until 2008. So quite a long period where I spent my study student life in Japan. So that's how we created this Nagoya University Alumni. Right. So allow me to introduce a little bit about our institution. So our university is called as this University Tun Hussein of Malaysia, or in short, we call it UTHM. It was established in 2007. Before that, we was known as a training institute for the polytechnic staff. So the history was started since 1993, and then evolved to become an Institute Technology Tun Hussein on, and then in 2000 it became a college university, which is small scale of university, we call it as college, and then it became a full a total university, full-fledged, so that we can offer more program at more students. So then we have this UTHM in 2007, and then we also have a branches campus, also still in this Johor area, so the southern region of Malaysia. So it's just quite a small branch campus that we have too. So our university is focused on this sustainable technology and transportation. So this is the key niche area for our university. So I believe myself is covering this sustainable technology. All right, so where do we located? You can see this is actually the southern region of Malaysia. The Singapore is added back down here. This is Singapore. So it can travel like 1 and 44 minutes from Singapore to UTHM. Okay, so if you want to go north to the northern region, to the KLIA, it will take like 2.5 hours. This is by car. All right, so then this is the map of our campus that we are here in this Batu Pahat region, in this Johor state. So this is 2 branches that we, as I mentioned before. So in this Muar region and also in this Tanjung Labu region. So it's not far, it's just like within 1 hour driving, these all branches. Right, so our total student is like 70,888, and 94% is local. And then our undergraduate is like 14,000, and 900 for master and 700 for PhD students. The international student, we have a lot from UAE and Indonesia as well. Like we have like 151 students right now. So most of them, I think they are doing master and PhD. Right, so our university is focused on the engineering, so that's why this is the faculty that we have here, the mechanical, civil, electrical and electronic, where I belong on this electrical and electronic. So technology management, technology education, computer science, applied science and engineering technology. So these are the core faculty that we have in the university. All right, for the research element that we have in the university, we have 5 institutes. So one where I belong is this Institute for Integrated Engineering. And then some other institute like Malaysia Research Institute for Vocational Training. So we also have the Institute Transformasi Sosial and Pembangunan Wilayah, so some transformation social program. So we have this Institute Ahli Sunnah wal Jamaah and also Malaysia Real Estate Institute. So under this institute, I2E, or in short I call, is this 5 center of excellence. So this is 5 center as well is supporting this institute. So I belong to this micro and nano center. On top of the center of excellence, we also have center of research, where this center of research belong to the faculty. So these are the numbers of some acronym for them. So they belong to the faculty, so they do research at the faculty. And also this focus group also belong to the faculty. All right, so this is our Center of Excellence, Micro and Nanotechnology Center. So we have our own dedicated building, all the facility, the deposition, the characterization tools that we have, everything is inside here in this building. So coming back to the issue that I would like to discuss here is on the semiconductor industry. This is a very recent article published by the newspaper in Malaysia. So discussing about the semiconductor Malaysia. So we know now I think since the COVID-19, everybody have transformed their way of communication. Before this, we do a lot of physical face-to-face conference. So for ICOPIA like this, we do have conference in Indonesia. So maybe we need to travel to Indonesia. But right now, we are more familiar with this virtual conference, virtual classroom. So everybody have been, this is a new norm since the COVID-19, right? So that's, and then because of that, there's a lot of sales of the smartphone, sale on the laptop, sales on the some tablets. So it become a very booming. So for that reason, we can see a lot of shortage of semiconductor, of IC, of integrated circuit. So a lot of issue have been seen since the COVID-19. In fact, we can see the sale of the automotive, the car is also increasing in Malaysia, because sometimes people don't prefer to use a public transport because of this COVID situation. So they want to use their own transport. So the sale of motorcycles, cars also increase. And that is become the shortage on the IC, the integrated circuit, the chips that to control the automotive or to some our electronic device. So we can see that's the reason why we have a very increase on the sale of the global chips. So you can see on here. So we can see that the increment is on par with the previous year. We can see the increase, the demand. You can see at the bottom chart here, the global chip sales cycle, you can see is increasing. So maybe I'm not sure, maybe you can achieve until like this figure in 2010. So the fact here is that the semiconductor industry, the IC manufacturing, the microelectronic industry has become a boom right now. So many demand on the E&E, electrical and electronic students. So we can see a lot of international companies such as Infineon, Intel, Nexperia. So are reinvesting in their investment in Malaysia. So you can see this figure. So this is a good sign. This is a good sign for our student and for our university, so that we need to produce more talents to supply to the industry. So you can say this is the map where we can see the Silicon Malaysia, we call it. So the international company that we have in Malaysia, so most of them here at the center here is the company that is located in this Penang Island. So this is so-called the Asian Silicon Valley. So we can see a lot of company like Intel, Plexus. I think I don't have to name it. You can see from here. So a lot of company on the semiconductor industry is focusing in this region. So also we have some other company like Texas Instruments, IBM, also in the Selangor, in the middle of Malaysia, Selangor and Kuala Lumpur, and some in just a little bit on the southern region. So this company have been in Malaysia since almost 50 years already. So this is their 50th anniversary this year. So quite a long journey they have gone through, and we have been experienced with this industry. So coming back to the plasma processing, the topic that I will like to discuss. So these are some of the useful textbook that maybe you can look into in order to understand about plasma. So number one is on the plasma diagnostic, and then we have this, I can say this principle of plasma discharge and material processing. It's like a Quran for the people that working in the plasma. So I think most of you will know this Michael Lieberman. So this is a very comprehensive book to discuss about the plasma. And then there is some very attractive lecture note, simple to understand by this Francis Cheng. So you can try to search on this book. It's available on ebook as well. So we can see what the evolution of the television, for example, when I was born in 1979. So this was the common. So nowadays we don't see this kind of television anymore. In the year 2000, we can see still have a very bulky television, and then in 2010 we don't see this bulky anymore. We have a very slim TV, very lightweight, and in fact it's become more cheaper, right? So we have like a plasma TV, LCD TV, and very recently on the LED TV, right? So this technology is very important. So this is also something interesting. I'm not sure whether the students here have seen this kind of cassette tape before. So this is where the way we used to listen to the song in the 80s, I think. So inside there is a tape. You can see, okay, what will happen when sometimes it becomes spoiled. So it become something like this. So then we have to make it proper into the cassette. So this is where before we have a CD, before we have a hard disk. So this kind of cassette tape have been replaced with a disk, with a hard disk. And then nowadays with a solid state drive, SSD, and now everything is embedded into our handphone already. So just inside our handphone, we have everything. We have the camera, we have the radio, we have the saw, we have the TV. We can watch a movie. We can do a lot of things with our handphone right now, right? So everything is embedded inside here already. So the key element of this memory is actually on this memory, how they are able to create a memory chip much smaller. So this is the example on the SD card. So 1 GB by Toshiba. So you can see the cross section here and the diagram. You go zoom a little bit, you can see a lot of gate, floating gate, substrate. You can see this is the scale is like 200 nanometer. So how they are able to fabricate this? So the keyword for this kind of fabrication is plasma processing technology. So without the plasma processing technology, we are not able to deposit, or we are able to do etching. We are not able to do this kind of fabrication. So what is plasma? for the medical, for the biology people, so they will think plasma as a yellowish fluid in the blood, and it make up to 55% of our total blood volume. Okay, it consists of protein, glucose, some other mineral. So it's a medium to transport the essential substance in the blood. So that is plasma. For physicists, I believe most of us here is a physicist. So this is a fourth state of matter. So we create plasma by adding energy to the gas, so that the electron can live and become ionized, and then 99% of the matter out there in the universe is in the form of plasma. Outside there, the star and everything, including the sun. Are made of plasma. So that is for physicists. So this is the blood plasma. Okay, this is the basic of plasma as mentioned. So when we heat a solid, supply a fire to the solid, and then we get the liquid. Okay, when we heat the liquid, we get the gas, and when we heat the gas, we get the plasma. So that's what we call as plasma. Sometimes they also call as ionized gas. So this is where the electron and the atom and the ion are freely moving. So instead of the gas where you don't have a free electron inside there, you don't have a free ion inside there. So it's different. So that's why the plasma have two characteristics. It's similar like a liquid, sometimes similar also like a gas. Aurora is also a plasma in nature. So you can see this in a high latitude region with the Arctic or Antarctic. So you can see that. I have never have an experience to see that. So there's also a hot plasma in a fusion reactor. Okay, comet tail, some kind of dusty plasma we call it. Aurora, the sun, and sometimes we can also create this plasma in the lab. Yeah? Most basic plasma that we can see from our daily life is the pentafloor lamp. I'm sure some of the building are still using this pentafloor lamp, because LED lamp sometimes is easy to spoil. So we can see this kind of pentafloor lamp still. So this pentafloor lamp is also a plasma actually. So there is a gas inside here. So normally they use I think they use a xenon, right? So and then the gas is the electricity is supplied to the left and right, where they have the electrode over there. So then we'll create a ionization inside here. So then the ion will bombard to the wall, where you have the phosphorus material at the wall, then emit a white light. So this is also a basic plasma that we have in our daily life. So the key point inside this plasma, we need ion, we need electron, and also we need neutral. So all of them have their own temperature. So this is also a unique, important property of plasma. So we need to understand what is the temperature of the plasma. So normally we call a cold plasma is have an electron temperature like 10,000 Kelvin. So it's like 1 EV. Yeah, 10,000 Kelvin, 11,000 Kelvin is 1 EV, 1 electron volt. So normally we use an electron volt as a unit to discuss about the temperature of the plasma. So this is a poster. I think I downloaded it from from Japan. Okay. So to explain the plasma that we use in our daily life. So on on the left here, so you can see plasma is used in TV for your light, LED. We can also the pentafloor. We can the burner they use for the cooking. Also sort of plasma. We have the laptop. All the IC chip inside the laptop is created by plasma. So you can see plasma welding as well. It's also a sort of plasma. Using a plasma for nanotechnology to grow things like carbon nanotube or some plasma enhanced CVD, chemical vapor deposition technique. So you can use also plasma. You see the lightning here is also a plasma. So in fact, the rocket jet, they are now using the jet propulsion. They are producing a plasma propulsion so that we can travel from Earth to the Mars. So they are exploring on that. So the sun is also a plasma. So I think there's also country, a big country like Japan, Korea, China, EU, India. They are collaborating to create the sun on Earth, a man-made sun. They call it man-made sun. So this is a plasma fusion. So they want to create this one to become a source of energy. This is the most cheapest energy that will be in the future. So if you watch the Avengers Endgame, okay, so who is your favorite characters here? It may be the Thor here. Okay, so my favorite character is this Iron Man. So because he used plasma fusion on his heart. So this is a plasma fusion. So where he used it to supply the energy to his device and also for him to live. So this is also another technology that is we can see. So as I mentioned, plasma is the ionized gas. So we call it cold plasma. If the ionization of the gas is like 1 to 10%, we call it hot plasma. Is all the gases are fully ionized. For example, if you have 100 atoms of gas inside there, so all the 100 atoms become ionized, and so you can have an ion and electron only. So that is we call a fully ionized, is called hot plasma. So sun is a very, very hot plasma, is fully ionized. You don't see the neutral gas anymore. But in lab, we are using a very cold plasma actually. So some article that we have published about how we can use plasma fusion using water from seawater. So these are the example of the plasma equipment that we can see in the lab. This is not my lab, just some to show you. So where you can see we have a lot of, we can have a lot of chamber, and then inside the chamber we can see the process. We can create the plasma. So this color here is belong to the plasma. So normally when you put argon gas inside here, it will 2 electrode to supply with the power supply, and then you create a discharge, as you create a plasma. So as a basic, how we can create plasma? So we can have a process chamber here. Okay, and then we can have a power supply connected to the one of the electrode here, for example, and then we have a grounded electrode at the top, and then we supply the gas into the chamber. So we can be normally we use argon gas through the mass flow controller to control the gas flow, and in order to make sure the chamber is vacuum, so first we have to pump all the air inside the chamber. We can use a rotary pump, some rough pump, some turbo pump, many kind of pump that we can use. Okay, then after that, after we have a vacuum inside here, we put the gas, and then we create a discharge through the power supply. Sorry about that. So this is some cartoon to show a world without the engineer. So you can see the kids watching the television on this paper, and then how we can do the communication. Yes, something with a wire and something like that. So without the engineer, without the technology, we are stuck. So why do we need to study plasma? So I can say the question here, can we live without a computer and a handphone nowadays? And more than half of the semiconductor IC fabrication require plasma. So therefore we need a designer, engineer, technician to know plasma behave, and then we need to develop a reliable plasma machine. Okay. Some fundamental info on the plasma. So normally in plasma we have a chamber. So this is normally a chamber. The plasma is we call as a quasi-neutral plasma. So because of the plasma at the core here is neutral, actually neutral. So you can see the example on the right here. So the number of electron, the number of ion is equal as the number of atoms inside here. So it's we call it neutral. But at the boundary, near the boundary here, the density of the ion and the electron is not the same. They are not the same because the weight of the electron and the ion are different. So the electron can move faster to the wall and become grounded there, and then that's why at the same time it will also attract the ion. So but since the ion is a slow mover, so you're not moving fast, so the density is a little bit higher compared to the electron. So that's why we call it as a quasi-neutral. So it creates a region we call as a sheet. So this is the boundary between the plasma and also the border, the chamber wall here we have here. So this is just like to show the cross section of the plasma. So that's why you can see the plasma is something like this. You see plasma at the center. It's not totally touching the wall. So you can keep the plasma inside the chamber. Some classic example how plasma processing is very important. This is an example of the silicon etching rate. So the removal of the silicon etching. If we use a gas only, or if we use a gas with a plasma. So this is example. If you use a gas only, for example, to do the silicon etching, we need a fluorine-based gas. So they use a XEF2 here. So we can see if you use gas only, the etching rate is just like below than 10 Armstrong per minute. Very, very low. You cannot do the etching fast. So etching is a process of removing the silicon. So this is one of the important process for IC fabrication. So if we combine XEF2 with the argon ion, you can see the silicon etching rate increase very rapidly up to more than 6C Armstrong per minute. And then when they use argon beam only, it reduces back. So this is to show that chemical and the plasma process here is very, very crucial in order to use it for the microelectronic fabrication. So we can use for the silicon etching quite very fast. So that's how the plasma is very common nowadays for the semiconductor industry. And this plasma processing can be used for etching, can be used for plasma enhanced chemical vapor deposition, can be used for sputtering, ion implantation, plasma spray, medical sterilization, etc. So now there's a lot of application. So this plasma processing is also very critical. Before this, all the researcher, all the industry, how they control the plasma process is by control the parameters. So they control the power, the pressure, the gas flow, also maybe the design of the chamber. So this is before. And nowadays, we would like to propose that instead of controlling this parameter, so we should control the fundamental inside the plasma. So we should control the density of or the temperature or the velocity or the energy distribution of the ion and radical inside the plasma. This is what have been proposed by the Plasma Society. So just skip this one. So this is some example how they, so if you want to understand more, so there was a plasma roadmap have been published in 2012. So where they discuss about how we can use plasma as, and then we can monitor the plasma, we do the real-time diagnostic, and then we go feedback to the system, and then we can go very smart. This is example how they grow the, this is a carbon nanotube wall, right? And then they should be able also to integrate all the system here. This is modeled by Applied Material, so we should integrate this device. So one of the key person here is this Professor Saniski at the center here, where he developed this kind of plasma diagnostic. So he is one of the contributor for this article, and where he discussed that in order to understand plasma very well, so we can study by from the emission, we can study by the scattered radiation, we can study by the absorption. We can also put some sensor inside the chamber. We can also put the probes, so we can collect the electricity from the plasma. So these are the way that we can do this kind of plasma diagnostic. And then after 2012, then 2017, they produced another roadmap. So by understanding more development on the plasma. So there's a lot of new type of plasma device. Sometimes they call it as microplasma, pulse plasma, or solution plasma inside the liquid. So we can study the characteristic of the plasma, and then we can integrate them. So we have a system of plasma source. So a new plasma science and technology have been proposed through this roadmap. In the future, there is many more application of plasma science and technology. So this is some article that have been published in 2018. So where they show that plasma is useful for environmental as well. Why? We can use plasma to expose to the seed, so that we can enhance the growth of the agriculture product. So it can also use for the health application, for the sterilization, for the plastic and textile, do the coating. They can use it for the aerospace and automotive as well, and also to produce energy supply like a solar cell. So this is also an example of figure to show where the plasma is used for the coating on the glass, on the camera product, on the laptop, some bags, glass as well. So these are the application. So for a plasma nanoprocessing, we need to understand the plasma physics, we need to understand the surface chemistry, and then we need to understand the plasma chemistry. So this is every process is complex. So we need to understand these three conditions. So this is some of the plasma source that is available in the market. We call it, start from the right, is a helical plasma and the electron cyclotron plasma. So this is the type of we call as a high density plasma, where the density of the ion inside this plasma is up to 10 to the power of 14 per cubic centimeter. So it's quite very rare, this kind of device, but for the sun to produce energy, high energy, we need this kind of high density plasma. On the left is so-called as a low density plasma, where the density is like 10 to the power of 11. 10 to the power of 11. So you can see that the type is like ICP, if you are familiar with the plasma. We have a CCP, capacitively coupled plasma, and also magnetoscattering plasma. So this is just a figure to show the example of the ECR plasma, helicon plasma. So you can see here, quite very bright and high density. Okay. So ICP plasma is very common. Okay. PVD is physical vapor deposition. It's very common for the coating application. So they use it, for example, this is on the right here. You can see they want to put the tools, the drilling tools. So they put inside here so they can deposit titanium. So they put the titanium plate at the right and the left here. So they put the gas of argon inside and then the discharge so that the titanium ion here will evaporate and go to deposit on the drilling tools. So they will create a hard coating on the drilling tools. So the material normally they use titanium nitride, titanium carbon nitride, TiAl, titanium aluminum nitride, and TiZrn. So normally the nitride film is a hard coating material. So we do a lot of this kind of sputtering experiment here. So sputtering is a process where you have the argon ion and bombard on the material, and then they will eject. You will eject the secondary sputter particle. Okay, so you can see on the left here. So this is an example where you have a material is now vaporized from the target. So we use this one for the growth of the solar cell material actually. So the solar cell material that we want to focus for this project is on this. We call as CZTS, copper, zinc, tin, and sulfur. So CZTS as a new material to replace the CIGS existing material, because the CIGS, the existing thin film solar cell, is a rare material, not abundant. So we want to replace it with a more abundant material. So we call it CZTS here. So abundant, non-toxic process. So we propose, you can see that this is at lower cost. But the issue is in this CZTS material is because of the less abundance of S in the thin film. Because the sulfur is a highly vaporized material. So when you put inside a vacuum chamber, it's easy to vaporize. So that is the issue. So that's why we think that we need to understand how the sulfur can go into the thin film. So this is an example. So where we deposit the CZTS thin film on the glass. So we can see a very good uniform thin film here. So, and then we also see when we increase the gross chamber, the chamber pressure actually. So this is 3 millitorr, 5 millitorr, and then we increase like 50 and 100 millitorr. We can see the surface become some like nanoparticle on top of the smooth surface. So by study this particle morphology, chemical composition, we can see that the sulfur is a lot on this nanoparticle. So meaning that to show that higher gas chamber pressure can contribute to a lot of sulfur content inside the chamber, inside the thin film. Okay, and then when we study the Raman shifting, you can see that for this nanoparticle have a very good crystalline, but on the flat surface here, the film is like amorphous, right? Broad spectrum you can see here. So in order to understand this growth of CZTS material, we use ultraviolet absorption spectroscopic technique to understand that. So we have a hollow cathode lamp on the left, and then the light source is injected into the chamber. And this chamber, we have the CZTS material or CZTS plasma inside here. And on the other side, we have a monochromator, spectrometer to collect the spectrum from this light source. So the plasma will absorb the light here. So then we can understand how many density of the material inside the plasma. So this is the result where we evaluate the sticking coefficient of the sulfur atom. So we evaluate for the tin, for the sulfur, for copper, and also zinc. So as a function of a gas pressure, so we can plot this decay time of the each element. So by having this equation, actually, so this is a common equation for the this decay of the atom inside the chamber. So we can actually evaluate the sticking coefficient. The sticking coefficient is a number to show how the particle, when they touch the surface of the silicon, whether it stick or it's move away. So if the number is 1, meaning that it go touch to the silicon surface and then it stick over there. If the number is half, meaning that second time it touched, then it go stick. So that is we call as a sticking coefficient. So this to show that the result that we found here, that sticking coefficient for sulfur is less, which is 0.7. So that's why the sulfur is not high in the content of the thin film that we have here. So by comparing the EDX analysis of the sulfur content here, we can see the sulfur content is less than its stoichiometric. The stoichiometric should be 50%. But when we do the EDX analysis on the CZTS thin film that we developed, is less than 50%. So this result is consistent with the absorption analysis to show that the sulfur is 0.7 is taking probability. So that is the reason why the sulfur is not up to the stoichiometric 50%. So we also have this chamber in the UTHM. So in this sputtering chamber, we have two types of power supply, radio frequency and also a DC, a direct current one. So we have a target, dual target. We have a 6 viewport. And okay, this is a very conventional plasma. So this very bulky chamber is quite costly. So, and in order to, for the future, so they want to create a plasma without this kind of cost. So the conventional one, we need a chamber, you need pump, you need gas, a lot of cost. So how we can create a more cheaper type of plasma? So this was introduced, the first, they call it atmospheric pressure plasma, APP, in 1857. So where this researcher, Simon, create a discharge when they create the oxygen gas into this tube, and then the electricity through this transformer supply to the tube, and then they create the ozonized oxygen. So this is the first, very, very first atmospheric pressure plasma. And you can see here, this is to show that very lot of type of oxygen atmospheric plasma. So they also call dielectric barrier discharge plasma, DBD, and also atmospheric pressure plasma jet, APPJ, a corona discharge, flame here, some type of plasma as well, ICP type and arc discharge. So the plasma welding is a type of arc discharge. It's operated in a atmospheric pressure. They don't need a vacuum chamber. So this atmospheric pressure plasma is useful for the treatment. Now you can see this is the example where the Professor Friedman from Drexel University United States, they expose the plasma to the tissue. So when the one we're exposed with the plasma, you can see it's not spoiled, it's not broken. So we can, this is the non-exposed, but this is on the right is the one that exposed to the plasma. So no damage after when we do the treatment. In fact, they also use it for the whitening on the teeth. So you can see on the left is a teeth with and without exposing to the plasma. So on the right here is when you expose it to the plasma, So you can see it's a little bit whiter. So the control one is a 1, and much more significant for the red wine. You can see here, the one that exposed with the plasma become whiter. So before the treatment, it was like this. So they are now proposing this microplasma for the this treatment. This is not pain, completely no pain. So that's why it's very, very useful in the future. So atmospheric pressure plasma can be used for the this kind of surface reactive species, and create a charged particle, create a thermal radiation, create a EM field, some UV light, and some visible light as well. So the application can be used for tooth whitening, surface treatment and modification. Nowadays, they are also proposing for the cancer therapy, air and water treatment, blood coagulation, wound healing, and many more. So we also develop our own plasma jet, very simple one. We use a neon transformer, connect with 2 electrodes inside and outside. And then we have a quartz glass tube, and then we supply with the gas of argon, so that we can create a plasma jet here. So this plasma jet we expose to the E. coli bacteria actually, and where we collect from the wastewater. So then we study, this is the result, the control sample, and then when we expose with 10 seconds, 20 seconds, 40 seconds, 60 seconds, and 80 seconds. So we can see when we expose this to the plasma jet, almost all the E. coli was inactivated, all in just like 1 minute, 1.5 minutes. So this is the summary. So we can see we repeated several times the experiment. So we can see the actually we change the distance between the plasma and the E. coli bacteria. So we can see on the left is at 15 mm. So we can see in less than 1 minute, you can see the bacteria is inactivated. If we put a little bit distance, so like 20 mm, so you can see the bacteria is saturated like this until these numbers, right? So we need to put that, we need to fine tune the distance as well. So in order to understand whether the plasma, this radical species or the UV light or the heat from the plasma, they're actually killing the bacteria. So we do some simple characterization on the temperature. So you can see the temperature at the electrode, the sample here actually is not high. It's like less than 40 degrees Celsius. So in order to understand what is the one that killed the bacteria, so we study using the optical emission. So we have the spectrometer here, monochrometer here. So then we observe the spectrum. So we can see here, so at this same distance, 15 mm, so we can see a lot of UV emission in this region. So this will be the reason for how we are killing the bacteria. So the cost of the device is very cheap. It's like 300 ringgit, or it's less than $100, of course. Okay. So atmospheric pressure plasma is an innovative and promising technique for super fast treatment technology. However, there is still some issue and challenges. For example, the reactor configuration is not feasible. We have to redesign it. The cost and the lifetime of the power supply also some issue. So physical and chemical property during the treatment. So we need some changes. You can see that. And then in order to upscale it, so it's a little bit challenging. So as a summary, I can summarize that plasma processing technology is still in high demand in the industries. Smart plasma diagnostic technique has been introduced. Atmospheric pressure plasma jet has been introduced to inactivate the E. coli bacteria. So thank you for that. And if you have any question, I'm very happy to listen to that. And you can also email to me at nafa@uthf.edu.my.
Okay, very nice presentation, Professor Nava. Thank you very much. Okay, and this is the second presenter delivered by Professor Nava. And I call for our audience to ask question to both presenter, for Dr. Acep Furqan and also Professor Nava. Okay. One question have already in chat room. This is from Muhammad Irfan. Okay, Mr.
Sure, sure.
Okay, this is one just how actually the FT work in your research. Thank you, Mr. Acep.
Okay, thank you. This is a very good question, yeah, from Muhammad Irfan Nawawi. I can share the slide. Okay, for example, this one, yeah, we already implement the calculation using DFT. Yes, there are so many potential to check the best one, yeah. We still use GGA. As you know, GGA is still assumption from the ground state, all item in the ground state. You can see here our calculation using DF calculation using DFT. We can get this number. Yeah, we can get this number, for example. Yeah, gallium nitride with ER and with TM, for example, like this one. And other researcher in the world, in other paper, they calculate also the result look like this. Yeah. And the experiment, they can get this one. I think this is good enough. I mean, good agreement like this one. But maybe you can ask yourself, why still different like this one? Yeah. For researcher, there are not enough question. They always make a new question. How to explain the difference of this one? Yeah, I think still different 0.05, like something like this one. Yeah, 0.105. Yeah, 15. Yeah, 0.15. So yeah, every question can create new model actually. Yeah. So this is actually still use general DFT using GJ. If you can check, so many people try to propose the better potential for their interaction. Yeah, including you also can propose new potential to explain, as long as it can explain the experiment. Yeah. So I think it's this calculation is fair enough. Yeah, still can follow the experiment, and it can explain the experiment. But you are want to more and more. Yeah, how to make this more? Of course, you can imagine in the reality and experiment, not really 100% in the ground state. Yeah. There are still some interaction there. Yeah, that's why you need other idea to explain out. I mean, try to find the best potential you can explain. Yeah, for example, if you can use another potential, of course there are now many options. Yeah, And using the use potential, you can close enough with this number. It means your potential is work better than the other potential. Yeah. The important thing how to explain. Yeah, because not fully 100% in concept explain in experiment. Yeah. So it's becomes strange if you can find this number very close to this one. Yeah. It's stranger. I mean, more strange. Yeah. Because it's still use in ground state assumption. Yeah. But the best one is of course in experience, but you need more other potential candidate. For example, the candidate who can 10% interaction or 20 interaction. What kind of interaction? You can propose new idea about the some kind orbital, yeah, in F orbital, something like that. Yeah. It's very interesting for this one. Yeah, and I suggest you don't satisfy with your result, and you need more explanation. Using this one, you can get more better better calculation, plus very match with the experiment result. I think, yeah. So using this DFT, it's really work, can follow this result, and you can check in another calculation as well. It's good enough to explain the calculation, the experiment. For example, I can see, yeah, like this one. Yeah, using this supercell, present calculation 2.1, yeah, and the experiment 2.23. The other calculation from the other people, like this one, 1, 2, 3, another paper. Also, they use they can get the best result like this one. Yeah. Why in the world cannot follow this result? Yeah, of course, in experiment, not fully 100% in ground state, something like this. Yeah? Because of course there are another interaction around this one. Yeah? So I think it theoretical is the best one. Yeah. If the result completely same 2.23, I am really not happy. Oppositely, because why? Yeah, because I think should be different, little bit. Yeah, and you need more. Try to find another candidate for the potential, because this is really ground set in GGA. Yeah? And you can, so without using other interaction involved in this calculation, it's really a good step for you. Yeah, I think that's all. I don't know, is it clear or not?
Okay, I hope that's clear. Okay, maybe one question for me, Mr. Ajab.
But it's very good question. Yeah.
Yeah.
If we get same number with experiment, it's more strange. Yeah, because it should be little bit, because we need more. I mean, every system have different potential interaction. Yeah, something like.
Okay, I hope the answer from Mr. Ajab is clear. Okay, there is some question from audience, from Rafi Ihsan to Professor Nafa. I heard about laser technology used in the field of medical treatment. Have you compared the effectively between how plasma versus another instrument? For example, laser ER work to reduce the coil. Okay.
Yeah, thank you. Thank you, Chairman and Dr. Rafi. So I think he asking about whether the laser, how the comparison, whether using laser technology to do the medical treatment. Maybe, for example, on the teeth, for example. So I think laser technology is also a much more developed technology. Used a lot for the LASIK as well. They also use it for using laser. But the disadvantage of laser is that is very, very bulky. To manage a system of a laser is very bulky. You need a very long range of device, and it's very sophisticated or dedicated person to handle the laser. So because sometimes you become dangerous. So if you don't specialize in handling that facility, laser facility. So that's why I think in order to, in the future, if we use a plasma, it's much more smaller in device size. It's much more easier to control. It's not as complex as a laser. And I believe that in the future, the price of the plasma jet will be much cheaper than the laser device. So in terms of efficiency, maybe the laser is much better because the energy that produced by a laser is much higher. You can do the treatment faster. But if you don't matter about the time, so maybe the plasma can be some alternative in the future. So plasma can be much cheaper, can be much easy to operate. So I think this depends on the what type of application that we want to use here. So that's the comparison between the plasma and also the laser type of instrument.
Okay, thank you. One question for me, Professor Nafa.
Yep, probably.
In your presentation, I get information regarding the use plasma for device fabrication.
Yep.
The plasma for film fabrication is commonly we know, but usually device fabrication by lithography techniques and also and other etching. How you explain the plasma fabrication in nanotechnology?
So as you mentioned, plasma is very common. So we use a lot for deposition and also for etching.
Yeah,
so this is two common, I think, application, right?
Yeah. But in your presentation, you use plasma also in device fabrication. What usually we use the lithography techniques and also etching.
Yeah.
What the position plasma device fabrication? The before lithography or after lithography, or on another place we use the plasma and nano device technology?
So when we do a lithography, actually we want to do the patterning. We do the design, right?
Yeah.
That is the process of lithography.
Okay.
So after we do the design, we need to do the etching.
Yep.
We do the etching. Is actually etching plasma is by using the plasma.
Okay.
Etching device is creating argon and the fluorine-based gas into the chamber, and they create the etching plasma. So that is how we use plasma. So the plasma is an atomic ionized gas. So they do the chemical reaction to the substrate, the area that we expose through the lithography.
Okay,
so then we do the etching.
Yes.
And then when we want to remove the photoresist layer,
yes,
PR layer, so that is also using the oxygen plasma. So to remove the photoresist material. So that's, and then after that, normally we want to create a metal contact into the chip, into the device.
Okay.
So to create a metal contact, normally we use a sputtering plasma.
Sputtering
Plasma to fabricate the. Normally we use titanium, aluminum, or some gold material. They use an evaporator. Then so this kind of combination lah.
Yeah.
So that's we use plasma.
Okay, thank you very much for your.
Thank you.
One question for Mr. Acep. Why select the rare earth element for your computation?
Sorry?
For your use the rare earth element for doping and GAN for your experiment.
What kind element?
Rare earth.
Yeah, all rare earth we calculate.
Yeah, why you just
Okay,
tell
okay.
us?
Yeah. It's very interesting because when you see the band gap not so high, but still a semiconductor. So it means we can get, if we use in large scale, it's very efficient. We can saving energy more than the current LED. Yeah.
Okay.
And the problem maybe still a little bit the price, but the price is economical aspect. But if we can make efficient in a synthesis of a rare earth in Indonesia, for example, we can reduce the price. So it means Indonesia can take a lead in the world actually for LED using rare earth. It's very interesting because we have plenty of material, mineral, than the other countries. Of course, the other countries don't have to focus for this one, but for Indonesia, I think this is a good chance, yeah, for us. Maybe this one.
Okay, thank you very much. Maybe another question from audience. You can ask directly by raise hand, or you can write down in the chat room. Okay. If you have a furthermore question, maybe you can direct email to Professor Nafa and also Dr. Ajab Furqan. Okay. Any question from audience? Okay, maybe there is no question from audience. I think this time is over right now. And I say to thank you very much for Professor Nafa and also Dr. Ajab Furqan. Very nice talk in here. Maybe another chance we can invite you another conference or another forum. Thank you very much. Okay, thank you very much.
Thank you very much for everyone here as well.
Thank you, Pak Asep.
Okay. Maybe
thank you, Nafa. Thank you.
Thank you.
Okay. The time is over and I return to Master of Ceremony.
Okay, thank you, Professor Budi Purnama, and also to our keynote speakers, Mr. Acep Purkon, PhD, and Professor Dr. Nafariza Nayan. And here are our appreciation sign for you. To the Honorable, our keynote speaker, Mr. Acep Purkon, PhD, and also Professor Nafariza Nayan, and also to our moderator, Professor Budi Purnama. Okay, before we continue to the next plenary, I'm going to welcome our moderator, Mr. Surja Kusuma, MSE, as researcher in Disaster Research Center, Research and Community Services, Universitas 11 Maret to carry this session. And besides, we have Lieutenant Colonel of the Indonesian Navy Operation Corps, Dr. Dian Adrianto, MSE, and also Dr. Andes Iwan Yahya, MSE. Could you hear me, Mr. Surja?
Yes, clearly.
Okay, thank you. Okay, Mr. Surja, time is yours.
Okay, thank you, Ms. Safa. Good afternoon, everybody. Ladies and gentlemen, distinguished guests, keynote speaker, and also researcher from Department of Physics, 11 Maret University. Let me first introduce myself. I am Surja Kusuma from Disaster Research Center and also a lecturer in Department of Physics, 11 Maret University. Welcome to the 8th and 9th plenary session. We have two speakers in this session. There is Lieutenant Colonel of the Indonesian Navy, Operation Corps, Dr. Dian Adrianto. Good afternoon, Dr. Dian.
Good afternoon, Mr. Surya.
How are you? Yeah. Dr. Dian will present the study of the wave characteristic at western part of Java Sea. And also the second speaker at this session, Dr. Iwan Yahya, a researcher in Department of Physics in Laboratory of Acoustics, 11 Maret University. Dr. Iwan, can you hear my sound? Halo, Pak Iwan. Yeah, maybe not joining yet. Dr. Iwan will talk about sustainably large aperture metamaterial with skew angle cellular structure. And ladies and gentlemen, at first, I will introduce Dr. Dian Adrianto as a first speaker at this session. Dr. Dian was born in Mojokerto, March 5, 1970, and the first education is in Brawijaya University as Department of Physics, and then Master Science in Institut Teknologi Bandung, Department of Geophysics and Meteorology, and the doctoral course is taken in Institut Teknologi 10 November, Surabaya. So Dr. Dian and Dr. Iwan, you have it's 30 to 40 minutes for presentation. And first for Dr. Dian is time is yours.
Thank you for the moderator, Mr. Surya. Is my voice clear?
Yes, very clear, Dr. Dian.
Thank you very much. First of all, I would like to thank the Honorable Professor Dr. Nuriani as a chairman committee of ICOPIA 2022. Secondly, I'm really glad and that time is offered me to be a speaker in this activity, in this conference, because Mr. Sunyani was as my colleague in MIPA Brawijaya University. Good morning, good afternoon, ladies and gentlemen. Also, for all the invited speaker, and also all the participants wherever you are. This is the first time I joined the international conference like this, so I'm glad can share my experience, can share my knowledge to the public community, especially for the young scientists. Hopefully in the future, hopefully there are a person that follow and develop my research, especially for the marine community. Can I share this presentation, my slide?
Yes, you can directly set screen.
Okay, thank you. Can you see the slide?
Yeah, already see.
Okay, thank you, Mr. Surya.
Just click the share screen.
Yeah,
Yeah, okay.
Sorry for a moment, please. Okay.
Yeah.
Before I start my presentation, I would like to introduce myself, even Mr. Surya did. I am Dian Adrianto. So my presentation, which based on my dissertation that supervised by Professor Dr. Eko Jatmiko and Professor Dr. Suntoyo. The title is the Recent Time Series, a Significant Wave Height Haze Dataset for Establishing Formulation of Spectral Wave Energy Density Characters in Western Java Sea. So, I would like to introduce my office. I work in the Pusidrosal, Pusat Hidrooceanography TNI Angkatan Laut, that provide the navigational chart and located in the near tourism famous place, Ancol. If you can require the navigational chart, you can contact me or visit the Pusidrosal website. So this is my office, and you can visit me, and if you have activity in Jakarta in my office, is I really welcome to, especially to discuss the my research. Okay, my outline divided four things. One is device preparation. Number two is measurement in the field. Three, processing and analyzing data measurement. And number four, establish wave spectrum energy density formula. The point is I accept the offer of Mr. Professor Sunani. That's, I hope there's no much opportunity to join with this activity. So based on my research, I hope the young researcher will develop and follow this method, because the research based on the personal funding. You know that if we conduct the research in any waters in Indonesia, need max funding, you know. So that's why this is, I think, this other way to conduct the research in the Indonesian waters. Okay, I continue with my talk with give some background. We know that Indonesia is the largest archipelagic country and have more than 17,000 islands. And based on the static position between two continents and two oceans, that's why the many people, or the most people, especially in the coastal community, significantly derive from the sea. So when we doing activity, any activity in the ocean, actually we need the information and the data about environmental to make running well our activity in there. But unfortunately, there are many accidents that happen in the sea caused by bad weather. So based on this, we have to improve and increase to understand about the weather, especially in wind and wave. Okay, we can see the slide, the Indonesian area that have the variability in a water environment. My point in my talk is how to conduct the research in low cost and long-term measurement, and hopefully the data that we get will have a good and accurate data. So we can process analyzing the accurate data into a good information which support our activity in the field. Sorry. I give the example for different point. and located in surrounding Indonesian waters. This point have located in southern hemisphere and have deep sea and open sea, and actually have a swell from far distance. And this one is located in northern hemisphere and deep sea, and have more than 15 meters depth. And you know that this Makassar ship passing through Indonesian through flow that make different quality of characteristic of the waters. So this one is northern ocean with deep sea and have 500-meter depth and inlet waters, and the unique is have high red tide. So actually, this one is the position of our research. So if we look at this slide, that we know that the variability in Indonesian water is very high or very dynamic. So we have to develop our research and get the information better and better. Because Indonesia consists 70% approximately based on the waters. Okay. The next slide, the question is based on the 5 points. One is how to provide accurately information about the environment and weather in all Indonesian waters. So, number 2 is how to get long-term wave data, minimum based on 1 year or more wave measurement. 3, how to modify a wave meter device from any available devices, for example, tidal meter. So it can be modified into a device that deserve and properly run in the field for a long time measurement. So number 4 is how to process and analyze the long-term big data and accurate information based on the deserved modified device. So the last question for research is how to build mathematical formula for the wave spectrum of energy density that represent the wave characteristic in any waters in Indonesia, especially my research based on the Western Java Sea, Indonesia. So why we need the origin mathematical formula in any water is Indonesia? You know that based on the scientific field, especially for marine engineering, this formula need to establish any structure, especially in the coastal area or the offshore. So that's why, hopefully, in the future, my research can inspire the other researchers, especially the young researchers, to develop and run the many research in the Indonesian waters. Okay. The next slide is what is the benefit of the research? The final research can be used a new reference in academic interest or sales knowledge among Indonesian scientists, especially for the same competence to develop further. The final result of research, especially in mathematical formula, can change if we sure that develop this original formula in the certain area in Indonesia water. We can use it in to build any structure in offshore and coastal area. Number three, the benefit is as a reference for designing offshore platform, developing with marine engineering, etc. So the last benefit, I think, perhaps there is more, the benefit more than four. I think is the main benefit to demonstrate and inspire young Indonesian scientists and researchers to increase confidential level to conduct such research with personal fund. So the point, my talk is one of my point in my talk is how to conduct the research in surrounding in any area in Indonesian water with the personal fund. We can compare with the data that we set in the field based on the personal fund and the modern method using modern water instrumentation, we can compare. So, excuse me, can I drink for a while? Okay. I try to break down the outline based on the conducted research. You can see from this, but I don't explain in detail because the main point in my presentation how to establish the formula mathematics, especially in base spectrum energy density. So the first step is preparation of the device. You can see the flow chart and the slide. The preparation of the device, the step activity is choosing the device, modify the device, and before we can use in the real field, in the long-term measurement, we have to make sure that the device which you modified is deserved and properly to conduct and use and the measurement in the field. So actually there are three tests. One is a laboratory test, and the second one is the 3 days field test, and the last test is the 5 days test to make sure and to refer to make to just to make sure that the result of the data have the accurate and deserve to conduct in the ocean. This one is the location of 15 days simultaneous test. The modified device, I gave a name MUSG, modified ultrasonic device, carried out and measurement together with the other devices. Three of us is tidal device and one is wave recorder device that located in the same area of waters surrounding is Jakarta Bay. So it was is in Marina tidal device. This one is the Putri Duyung. This is a modified device USG, and this one located in the Kolin Lamil, and the last one is located in Bodok Dayung. This is accompanied by wave recorder device that put in adjacent of this USG device. So I need to share that the result of the laboratory test and the second test in 3 days test. So you know that the result of the data is not properly. We have some error there, and you can see like this. After 49, 51, and jump to 27.6. So that's why we need to repair again and modify and check any component to make sure that the device will be run properly and deserve to run in the long-term measurement. So the last test you can see from the slide, located in the Lay Bridge, Ancol, Putri Duyung, Ancol. This for 5 days, 15 days measurement. Okay. After this, the 15 days measurement, we can separate, process the data with separating the tidal data and the wave data. This one is so that the tidal data, the wave data between RB2 wave recorder and the mu-SG modified device. And you know, you can see this, the graph, the curve is similar between two of them. So this one is the tidal data among 3 of the other tidal data device. 3 of tidal device. So you can see this, the trend is similar. Even the marine is not appear to have different phase, but the other 2 of the device is similar too. After this, we can calculate with the with the Admiralty method to determine the constituent, tidal constituent. You can see from this. Yeah, you can see that the constituent is similar. So that's why we can conclude that the modified data USG deserve and properly to conduct the long-term measurement in the field. The next step is measurement in the field. The measurement located in the Western Java Sea, in this one, in the block Cinta complex, in the platform oil drilling gas belong to CIMAC. This one belonged in this one. And this one is the office of that commanding office to control the operation. This one, you can see from this, I located this USG device in this device, and I use the type tool to control and to measure the elevation of the waters. Can skip this one. So the next step is processing and analyzing the data measurement. So we can we can go at this slide with this data is like this, and after this we can process the data to format like this. The one column number 1 is the number of the data, and the second column is rate sampling. One to say is rate sampling means in 1 second we have six measurement data, and the third column is the time in seconds, and the last column is the elevation of water elevation. Okay, out of this, we can make a cube, and from the x-axis is the period, and the y-axis is the surface. After data, we divide in every 30-minute data, and you can see this sample is 30-minute data, and this below cube is the 5-minute data, like this. This data, before doing filtering for decrease eliminate the error of the error. This one is the data after we process with the filter. That is the Savitzky-Golay filter in the notation F13 and 30. This, you can see from this column, column number 5 is the raw data, and after the filtering with the SKF Savitzky-Golay filter, the surface elevation change in the like this. So after we filtering this, we can use the data from the next processing, and this slide can show that this is the result of the filtering. The raw data have many errors, and use the filtering data, we can make a smooth for this the curve. I will explain faster. And this 30-minute data after filtering data. So we carried out the analysis based on the single wave method and wave spectrum methods. Single wave method to get the wave representative data. In the method, analysis by the wave height and period, but the second method, wave spectrum data, represented by the wave energy density distribution. And the wave data recording is divided into each group. Each group consists of 30-minute observation. So we choose the highest, 1 day highest measurement that represent the 1 month's measurement, so that we have the 12 days measurement. So the 12 days data we divide and clustering in a group based on the 30-minute data. So we will get the 576 wave group. So based on this, the number of group, we will analyze and process in the second wave method and analyze the result. The single method used to determine single wave. There are 4 approaches that are commonly used. There's determined from one wave crest to crest, throat to throat, and with zero upcrossing or zero downcrossing. So we give that with the NC, TC, and etc. N is the number wave, and T is period, and H is height wave. You can see the slide. That's what I explained in the previous. One wave is you can calculate. We can explain from this, from true to true, crest to crest, and with the approaching data, we can choose the zero in the 0 point till 0 point. So the down-closing data 0 point to the 0 point. That's the form of method to determine the the wave. So this is the this is the example, the result of the processing of the data. The following table is table of wave parameter in June 2016, and column 1 contains the number of group. The column 2 is the time, and the column 2 to set is the number of wave, and etc. You can see from the slide that we calculate the tabling in the minimum, maximum, and the average. So out of that, we can make process more detail and to see the trend of the wave. We can see that for the numbers of wave, H, height wave, and period, and this is the spectra of energy density. This one is same. I will jump. Okay, as the result of statistical analysis based on the measurement data for a year and represented by a 12 days data that represent in 1 year, we get the result of determining the number of wave with 4 different NC, etc. produce the same value with confidence level of 95%. The rest of the remaining number wave in manifest in the form of the maximum wave. Number maximum is 982. And the second one, the statistical analysis result for wave period T, the result of determining the period of the T with 4 different methods resulted in very close values with a confidence level of 99%. And the wave period summary is composed of the maximum wave period is 4.26 seconds, the minimum wave period is 1.81 seconds, and the average wave period is 2.97 seconds. Next, the statistical analysis result for wave height. It is the summary of the average, RMS, and sinusoidal wave, and the summary of maximum wave height. You can take them from this. So the analyze the result of processing the measurement data, we can predict with the basic knowledge. And in this case, we can see that with elevation distribution can be approximated by normal distribution, and with height distribution can be approximated by the Rayleigh distribution, and with period distribution can be approximated by the exponential family distribution. Okay, the next step for the research is how to establish the spectrum energy density formula with analyze the numerous curve of wave spectrum. The field wave elevation data in the form of time domain series transform into spectra in frequency domain use the FFT function in the MATLAB. So we will get the 576 spectrogram in the frequency domain. So for using the established formula, we group it or we clustering height significant in the 3 parts. Number 1 is 0 to 0.5 meters. Number 2 is 0.51 till 1 meters. And number 3 is 1 to 1.5 meters. So I use the general spectrum, wave spectrum formulation. You can see like this, and I create the simple program with the Excel software like this, and use the different HH unit. It's A, B, double, yeah, angular speed, and we use the program in this, and we input this S in the program. So the red line is the result of the program, and the blue line is the curve from the data measurement. So we can see from this is have the blue line have one peak, and we can approximate with the curve red line from the program. That's the similar with the different S, the higher S, 0.678 meters. That's it. But unfortunately, this character of spectrum energy, so that it has two peaks. One peak is higher than the others. So we need small repair, establish the formula, re-establish the formula. Then say it's more clear if we use we see that the last cube and the highest HS. So overlaying this paragraph at the definition with general equation. Then continue with this. We do the next step. The next step to repair to try good formulation that appropriate with the curve of the measurement. The formulation based on the available formula of wave spectrum. This one is consists 8 formula, but all of the formula just have one peak. So after that, we use the next available formula. You can see on this, name the spectra 6 parameter equation by Yochi. This main formulation, as you can see from this, and the variability, the various formula that support, then we can change based on the surrounding area and waters, have the different 11 different formula. So based on the formula, we did use the measurement data and go in the same windows. You can see from this. This is the red. The blue one is the go from the data measurement, and the others from the based on the formulation of OG. So we can see from this among 11 formula, 11 proof, we have find the 3 formula that have the 2 peaks. Yeah, this one is the data measurement. This one is from 5, and the green one is from 10, and the yellow one is from 4. So based on the 3, we can rebuild the formulation and applicate in this measurement until we get the appropriate or the best curve, the best fit of curve. So the next step from the establishing formula is, you can see from this. I wrote that I rewrote this constant and variable with A1. I give the name of notation A1, and this one is A2, then etc. And I make a simple program that I showed at the previous slide, like this, and we can show that the simple program shows the similarity or have have the 2 peaks, this one and this one. You can see from the other different value from height significant. If we compare with the measurement data in blue line, then with the black line is have the similar peak, 2 peak. But unfortunately, we have error, some error in this, and not similar and not fit in the data measurement. So, as part of this, we continue with the next step to establish the formulation. You can see from this, we add the formulation in this constant 0.25 name Z, and we put in this, and we try and error method. We compute, and we can display from this. So you can see that. You can see that with the mapping in the green circle line is overcome the error. So that's why the next step, I think, is the last step to establish the formulation of the spectra. We use any constant here. For example, is 1, 1, and 1 is the different term is 1, and lambda 2 we noted with G2 and etc. We use the try and error method. We can enter in the formula that when we build. So after this, we can see that the curve is better to approximate the data measurement. You can see like this. The red line is the result from the simple formula. You can see from the 3 of ones, 3 of them. I mean, this is almost similar. Then from the middle range of high significant is almost similar, and but a cumulative for the lowest of the H significant or H significant is the have the error here. So after that, we put and change and try and run again and again until we get the best fit between measurement curve data and the curve from the program. And after this, we make simplifies all of the formulation. You can see from this. We calculate step by step. This one, we rewrite the formulation spectrum of OC that way with the value that have highest curve fit. So after this, we give some trick to simplify the formulas, the wave spectrum formula, until we get the until we get the formula like this, and this is the rest. What you call the variable is with the simple tricky. I give constant that's similar than this formulation. So I think it's the end of the how to build and how to establish the formulation. The formulation based on the data measurement in the field. This AD, this HD is the number without dimension, and this form similar than the OC form. So this explanation is the formulation. We give name in formula spectrum Adrianto, Jatmiko, and Sundoyo. So all of the research how to place the formulation based on the available formulation, we can write it the total discrepancy between Adrianto spectra curve with the FFT spectra was, I can see this. We have from approximately confidence level in 50% based on the 576 tests. spectroscopic fluctuation equal to 47 days or X.16%, and the second peak frequency is 28 or 5.86%, and the second peak of the Adrian spectra was less sharp as many as 25 days or 4.34%. And the MFT yet curve did not have a second peak is 11 days or 1.91%. It should be underlined that at this stage, that these difference have not reached a critical level, which means that they are. After that, the next step, the last step, is how to state the state. How the characteristic, how the program shows the perform if we give the input in the different or higher height significant. You can see from this one, we can give the input from the 1 meter to 10 meter. And the proof based on the information you can see from this, like this. Sorry. You know that this one is assuming from this for this. So based on the proof, it can be seen that the increasing value of HS directly proportional to the increase in the value of energy density spectra, and directly proportional to the increase in the steepness of which spectra. This one, steepness, more steepness, and inversely proportional to the grand peak of frequency. So I think we give and we rewrite in the from the table like this. The table we can see, and the differences of two spectra can see of this, and then we make a curve in the figure 6.14a and 6.14b. The analysis of the frequency difference curve is figure 6.14a shows that it has more than 2 meter curve and decrease linearly. This is linearly after we give 2 meter input, the growth linear sharp. But the analysis of energy density spectra, different curve in figure 1.14b, this one, shows that the energy density spectra increase exponentially after the range HS from 1.10. So the test based on the 1 to 10 meters X Newton, the test is sufficient to 10 meters with the consideration that the depth of the map and with research location is only 20 meters. 20 meters is the depth of the area. So the test of max 10 meters is realistic based on the Sanil and August 2008. So I think we come to the conclusion and my presentation come to end. The conclusion is before we end this presentation, we summarize that the most important point from the result of the entire series of conducting this research is the direct wave measurement program in the field proved to be successful with very satisfactory result. The predicate very satisfactory is supported by the following indicators. One, the wave parameter often have a level of confidence, which is manifest in the following percentage values, namely n equal to 95%, period T in 99%, and H more than 90%, and wave spectrum more than 80%. Second one, up to this stage, the Adrianto spectral formulation has been successfully determined as the spectral formulation that represent their characteristic in the West Java Sea. By only conducting research on a personal funding scale and modifying existing tool, it doesn't not prevent the conduct of similar research on other fields with good result. This is expected to inspire and educate as well as increase confidence. So I think it's all of my presentation. Thank you. I give back to the moderator. Thank you, moderator.
Yeah, thank you.
Wassalamualaikum.
Yeah, thank you, Dr. Dian. Very nice research and integrated ones. It must be hard to do this research. Yeah, you have to apply the wave matter in the Sunda Strait. So please stay for a while, Dr. Dian. We have discussion after the second presentation. So in the second presentation, I will invite Dr. Iwan Yahya from 11 Maret University, Department of Physics. Dr. Iwan Yahya, have you hear my sound clearly? Halo, Pak Iwan. Yeah, I can hear your voice. Halo, Pak Iwan. Yeah, maybe the computer can call Dr. Iwan Yahya to open the mic. Yeah, and for a while I will ask. I have a question for Dr. Dian. So, if you say that, oh yeah, already start. Yeah, Dr. Iwan, you have 30 minutes for presentation, and then we continue with discussion. Please, time is yours, Dr. Iwan.
Can you hear me, Pak Surya?
Yeah, very clearly, Pak Iwan.
Okay, thank you very much.
Pak Surya, thank you, committee, for providing opportunity for me to deliver this speech, to share our experience, our some little innovation on this field, to discuss on in this very valuable moment. So, ladies and gentlemen, you can see in my slide, this is what happened in our modern day life every day. We have a problem with noise. So this is the issue that I want to discuss with all of you today, and what we have done in our lab to solve this problem. 30% of European population is exposed to noise level above 55 decibel at night. So this is a very serious problem. You can see in the slide the 6 other reasons, 6 other problem that we have to think about this problem to create the valuable solution. I mean, control the noise, and we got a new value from our innovation. Secondly, we are living in Indonesia, so we have this one. You can see in my slide. We have many ways everywhere that in abundant, but Almighty God has never created waste, so we have to find a solution and turn the problem into the value. That is the idea that I want to discuss here today. So this is the presentation title. We are talking about new technology, large aperture material, but we build it with sustainable material with a skew angle cellular structure. I'm Iwan Yahya from Iwani Acoustic Research Lab. This is the part of a V6 department. You can find my mail, my problems, idea, and etc. Our university internationally recognized by GSTAR and physics department, globally accredited by ASIN. So this is my lab activities in briefly. If you see all the panel on the video is made by our student. Yeah, this is our project in UNS Hotel. So we are working in IRG from theoretical development till development of the products. We have a very good collaboration with industrial, including Brunke in Denmark, and we have conducting industrial services and many other services. This is the milestone of my lab. We started in 1977 and focus on full spectrum sun absorber R&D. From 2000 to 2015, we have some achievement, including parametric resonator pattern. We also develop power generating sun absorber. We have a small design omnidirectional turbine with very low torque, exhaust muffler, and on that period, we developed our own method and formulation for calculating the sun transmission loss. In the next period, from 2016 to 2018, we have developed what we call a slotted resonator absorber, sustainable sonic crystal, and we are conducting our business, our first business initiative with Pradita Dirgantara. And in 2018, we have a possibility supported by Brunke and Denmark to do our global promotion. From 2019 till now, we have a more advanced achievement, including another business initiative. We introducing the idea of a secondary local grating on meta atom. So you can imagine you have gratings on atom with locally, and also we conducting certification and noise measurement for an 219 aircraft PTDI, and the idea of multi-resonance single cavity resonator. Then I want to share with you today. If you see this video, this is the idea of secondary local grating in atom, meta atom. So with this technology, we find a new phenomenon, which is collimation. Spatial collimation attenuation is occur in the same time for many bands. So this is novel. So what we discuss for today, this is my presentation outline. I'll introduce what is the metamaterial, what is the industrial challenge, and our approach and conclusion. We start with the first one about metamaterial. This is I cannot provide more detailed information about this subject, but if you interested, you can download it from my ResearchGate's web page. If we are talking about sound propagation into material, three things will happen. The first one, we have the incident wave, we have a reflected beam, we have transmitted sound wave. According to the transmission wave, we have three different ways how to control the transmission wave. The first one, according to the resonance mechanism, and the second one is mesh control. It means we're talking about density, we're talking about impedance, and the third one we're talking about what we call as a coincidence. Coincidence happens when the wavelength of the sound wave inside the bending material is equal or same with the wavelength in the air. So interference occur, and then sound waves transmitted without any decay. It's particularly happen with what we call as structural Born noise. But the very interesting question: what if, as you can read in my presentation, if we can replace any material molecule with an artificial teraunit unit cell in order with much less to the wavelength? If it happens, and we'll see this a very unique phenomenon. This is we are talking about metamaterials. On the above picture, there is what is a common we can see in our daily life. But if the water inside the ponds, something very exotic and unusual will happen. You can see the fish flow above of the water, and the right picture what we call as clocking or as transparent in metamaterial. So what is the basic physics of this phenomena? Okay, before we talking about the physics, metamaterial by etymology is compound words composed of two terms. Meta, it means beyond, and material. So in other words, we can say metamaterial is a man-made material that you cannot find in nature, but it's a composite that created by man. It could be optical material, electromagnetic, acoustic, thermodynamic. So what is the key concept of this material? As we see this, we can discuss about any material depend on two terms, but I'll show you a little bit about the early historical background of this material first. The idea of metamaterial first time introduced by Indian physicist Jagadesh Chandra Bose, who find the very interesting about seriality, and this work is followed by Lindemann. But the first theoretical explanation is provided by Russian physicist Vasalago almost 1 century after Chandra Bose. This is the first explanation. This is the first fundament of this theory. Another physicist is a British professor that contributes many significant finding, significant understanding on this field. So both of them, John Penry and Vasalago, is well known as the pioneer in this field. So this is a basic idea when we are discussing about material. If we are talking about material with electromagnetic perspective, we have this one, what we call as epsilon and mu domain. If the electric permittivity and magnetic permeability, both of it is have a positive value, we call it a red-handed medium. It according to all natural material, is that has the such properties. But if the epsilon is negative, and then we are talking about electric plasma. When the mu is negative, we are talking about magnetic plasma. But if both of them is negative, and then we are talking about left-handed material. Left-handed material is regarded as metamaterials. So this is the basic idea. If we are talking about electromagnetic, all of us, we know what we fundamental equation in electromagnetic is Maxwell equation. So you can see here electric field and magnetic fields related with right-handed law. So the factor pointing is parallel to the key factor. Contrary, in metamaterials, the factor pointing or energy transmission path is anti-parallel to the K factor. This is the basic idea of the metamaterials. Idea of acoustic metamaterial firstly introduced by Liu in 2000s. You can see in the picture that the first resonance occurred on 500 hertz, which the dimension of the structures is much less compared to the wavelength. So it is impossible. We are talking with the idea of Bragg diffraction. So this is will not happen in naturally. From this finding, acoustic metamaterial has developed in many researchers and have last contribution. One of the idea of a new concept for metamaterial I'll show you or to all of you today. So this is the three main category if we are talking about the acoustic metamaterial. The first one is membrane based. The second one is Helmholtz resonance based. And the third one is coupled material using two material with membrane and side holes. Okay. Mostly, almost all scientists do this technique on design any metamaterial. For example, we are talking about Helmholtz resonance-based metamaterial, and then we can create what we call as electroacoustic model. From this electroacoustic model, we can compute, we can do simulation to know what is the resonance of the system. From those knowledge, I want to show you what is the current industrial challenge. The first one regarding to application in aircraft. This slide part of our project with PT Dirgantara Indonesia. Our left is part of the team. We are in charge for noise certification and internal noise measurement. You can see here in the left, we are measure the outside noise by using acoustic camera, while the noise inside the cabin we are measure with 50 channel beamforming. I'm very happy to tell you that our lab is the first lab in Asia that has opportunity to use the very new technology provided by Pure in Denmark. So we can measure the cabin noise and overlays the noise map with the picture of the cabin. When we do this project, we have a many challenging problem in nacelle, in cabin, in window, and also on how to develop a constrained space muffler for the aircraft. The second thing is related to high-speed train. All of us knows that we now have a new high-speed train in our country. Maybe by the end of this year, all people can try the new trains. You can see here we have a very serious problem with high-speed train. This is a publication from Chinese scientists. They are reporting about a Chinese high-speed train that moving fast about 350 km/h. If you see the picture, the whole parts of the car body has the noise is above 100 dBA. It's not quite easy to control. Last month we have this discussion with our local company, PT Inca and IMS, how to control the noise in and their train. So I mean, we have a very good opportunity to with our new finding for application in our national and or domestic industries. This is also challenging for Nissan. In the next slide, I'll show you how engineer in Nissan do the same research, but with different technology we develop here in our lab. So they are developed metamaterial with honeycomb-based designs. Okay, that is the Nissan technology by using honeycomb-based innovation. This is our solution. We are not develop our metamaterial based on common honeycomb design because this reason. Honeycomb Helmholtz resonator has many limitations, including single frequency response. If we want to get a multiple response, we have to working with multiple frequency or array technology. That is also cannot absorb the energy for higher order modes frequency. So our goal is how to develop multi-frequency absorption that also can absorb the energy of higher mode frequency with only a single cavity resonator. So that is our point. You can see here honeycomb and also Helmholtz resonator has the limitation as I mentioned before. And this is the basic idea of our technology. We are working with not only a single cellular structure, but we are using multiple various skew angle cellular structure in a single design. So grazing flow that happen on the structure can induce Helmholtz resonance, can induce interference cavity resonance, and also side branch like resonance. This is the data about the material under test. We are working with cardboard, single wave and two wave cardboards. The model thickness is around 40 millimeter. The depth is 100 millimeter. We are using a big aperture. It's around 25 to 25 millimeter. The test procedure is using transfer function based impedance tube according to SME 1050 by using Brenke 4206 impedance tube. This is the picture of impedance tube and the samples. I'm so sorry that I cannot provide a detailed diagram of this model because it is a patent pending for now. So this is the results. First one, on the first model, we are not using the large aperture, but we are using the same neck as a conventional Helmholtz resonator lens. But we have a very interesting result. You can see in this slide, we have 3 peaks over there. The first one is regarding to Helmholtz resonance. The second one is regarding to wall treatment, and the third one regarding to viscous damping of the material. In the right side, you can see the blue arrow that's indicating repetitive absorption phenomenon. It is it's mean that the interference cavities we put inside our model is working properly. The second model, we are using the large aperture metamaterials. You can see here, we have a wider and much better sound absorption performance. And also we have the similar phenomenon, high order modes is absorbed very, very effectively. So what is the explanation? I can give the explanation to you. If you see the red circles, it's indicated that cellular technology that we have developed has the similar effect to the phenomena that reported by Chang, that if you are working with narrow channel that has the same phenomenon with the sound absorption is occur on 2 adjacent frequency. This is the typical response if we are working with coupled duct, coupled tube, and also side branch resonance. The second ones, repeated absorption of multiple frequency values, it's indicating that the absorption is induced by same structure, but in different frequency. So first resonance, second resonance, first mode, second mode, third mode, fourth mode, something like this, like that. This is indicating our technology is working very good and successfully absorb the energy of higher order modes of the sound wave. Absorbing more than one frequency with single resonators is the thing that that provided by Helmholtz resonator or any other resonator structure that available now in literature. This is, so what I can say to you, this is a very, very novel finding. You can see here, we have decay measurement, insertion loss measurement using impedance tube. Our product is decay is up to 45 dB, while the Nissan technology is only 18 dB. So we are working with different technology, with different structure, different technique, but we have also much better performance compared to the honeycomb-based structure. So this is one of the idea. What is the application of this product? We have a discussion with our local partner here, PT Inca, and this is our solution for the train. Our metamaterial can be used for floor composite, wall blanket, and also sonic crystal technology we can use for solving the noise for the U-shape concrete on the railways. Conclusions. So I have shown to you that our multi-resonance single cavity resonator material has been built and tested successfully. The school angel cellular material can simultaneously absorbing low frequency, mid frequency, and also the energy of the higher order modes. That is the very important finding of our work for these fields. I think that is the end of my presentation. Thank you.
Yeah, thank you, Dr. Iwan, for the nice presentation. And ladies and gentlemen, distinguished guests and participants, and now we have a time for discussion from the presence of Dr. Dian and also from Dr. Iwan Yahya. In the chat box, there is one question for Dr. Dian. I'm sorry if I am wrong, but I saw that Dr. Dian data have taken at 2015. Are that your experience results still relevant with condition wave in our sea wave today? How long is the duration of the data can accept for forecasting sea wave behavior? The question is from Dr. Fiska from University of Haluoleo. Please, time for yours, Dr. Dian, for answers.
Thank you. Thank you for the moderator. We meet again, Dr. Fiska, because she is, I know who she is. I know the family. Kita bertemu lagi. Okay. You're right. My measurement conducted in 2015 until 2016. How to determine the characteristic wave in any waters in Indonesia? We cannot determine directly with just for the 1 year data. If the characteristics of any area, any ocean, I mean any ocean in the certain area is not easy to change in 1 year. I mean 1 year is refer to the monsoon climate. So that's why at least we have, if we have 1 year data, we can use the data from the certain ocean, but at least, but it's not enough. We need the confirm in the next long-term measurement. So it's better, the better we have long-term data, the better as well we get the good information about the characteristics of the wave. I think that's the question. Thank you.
Yeah.
I think that's the answer. So
there is one question again for Dr. Dian. Directly chat to me. Excuse me, I have a question for Dr. Dian. What kind of sensor that you use to detect the wave regarding to the implementation inside the waters? How to maintain the function of your instrument? What kind of sensor and how to maintain the sensor?
yeah, thank you. From Mr. Bima.
Bima, yeah.
Yeah, actually I already answered from the chat room, but I will answer from this. Yeah, actually I have a team that didn't modify this tidal device into the wave recorder. So I don't know exactly, but the instrument, the component I mean, is easy to get in the local market in Indonesia. So if you want to get the more information, we can communicate by email, and I will send you the specification. Number two, how to maintain the function. Yeah, actually, when we conducted the measurement with the device like ultrasonic device, we have to protect with the weather. So that's why we put this device in the area, the second floor. There is the platform that have the, if I'm not wrong, is approximately four floor. That I put in this sensor in the second floor. So that's why, and I assume that it will protect from the bad weather. So the second one is the most important thing. We have to protect this device from the criminal activity, from the fishermen maybe. I think that's all my answer. Thank you.
Yeah, thank you, Dr. Iwan. Question for Dr. Iwan Yahya. The design is designed for the honeycomb in 0 degree, but your design is varies from 30 degree, 45 degree, and 60 degree. Is it right that you modify the degrees of the sounds 30 degree, 40 degree, and 60 degree? Is it right, Dr. Iwan?
No, actually, we can working with any incident angle of the material, but we have there's another consideration with the structure, how to what is the proportion of the sound wave that come directly in your cavity? What is the proportion come as a side branch like resonator, and then how you should think about the effect of interference cavity, because this thing is the key concept of the technology. If you are working with a 0 degree sound incident waves, if the end is close tube, and you get a quarter wavelength resonance. But if it is open end, it is working just like a conventional handheld resonator. So this is a very important thing to consider. First one, how many proportion of the sound wave energy that you want to absorb with a Helmholtz resonance mechanism, with side bands like resonance mechanism, and the third one with interference cavity resonance mechanism, because we are talking about grazing flow. You guiding the sound wave with cellular structure, and then also happens there's what we call a slow wave phenomenon. How to give phase differences between the sound wave that propagates in the different parts. That is the answer.
Yeah. Okay. And I saw the your presentation that in the high speed trains, then the noise is very high. There's more than 100 dB.
Yes.
Yeah.
Yes.
Almost 120 maybe. Yeah.
Yes.
And the area that that's very noisy is from the wall. So your purpose is to to install the honeycomb design in the all of the wall trains. Is it right?
No. We have another solution for the floor panel. We are working with different design for floor panel for the train. We have a technology, what we call as a sonic crystal innovation. So that we can absorb the energy of the sound wave from the boogie, from the track, reflective wave from the U-shaped concrete on the both side of the track by using sonic crystal technology. But this technology of skew angle material, you can put it inside the car body structure. So we can absorb the sound wave energy is much more effective to to all current technology that that available on the market. For your information, the standard requirement for our trains industries now, they are requiring the noise criteria is around CT 30 dB. That is much more less than comparing to our achievement. So I'm very optimistic. In the near future, we can do the much better. We can provide much better sound absorbing technology for our domestic industries, and
yeah,
that's it.
Yeah, thank you, Dr. Iwan. There is one question in chat box. I'm interested to your presentation. You said you have been working in developing aircraft using your research. Could you tell how exactly you tool used into the aircraft?
Okay. According to N219 aircraft, we are in charge for conducting the external noise certification and also measurement of internal noise measurement. We are not involved on the development stage of this aircraft, this new aircraft. We are invited by PTDI with agreement with approval from our authority, the GCA. This is we have already done this project 2 years ago. We have supporting from our global partner in Denmark, Care. As I mentioned to you before, our lab is the first lab in Asia that using the very new technology, spherical beamforming with 20 microphones on the sphere, including 12 camera on that technology. So we put the beamforming inside the cabin, and then we can measure the noise map all over the surface in the cabin, the random, the tonal noise, and everything. Outside the aircraft, we put another acoustic camera provided with another supporting from Norwegia, from Norsonic. So we can measure all the noise. We are also conducting in-flight testing by using our BNK handheld analyzer. So we have lots of data, but I cannot tell you about the data because we have an ND agreement, non-disclosure agreement with the company. So, but I can tell to you there's a many challenging problem that asking us to create a solution for this field.
Yeah, I hope that's answered the question by Arnesta Kusnawati. Yeah, thank you, Pak Dr. Iwan and Pak Dr. Andrianto. I think the time is up, and thank you once again for your nice presentation, you sharing your works, and I'm sure that is very useful for all of the participants. So if the participant want to ask a small detail about your research, you participant can contact you directly.
Okay.
Once again, thank you, Pak
welcome.
Thank you, Pak Dian.
Thank
Terima
you.
kasih. And back to you, moderator Mbak Haya. Silakan Mbak Haya.
Okay, thank you, Mr. Surya Kusuma, and to our speakers, Lieutenant Colonel of the Indonesian Navy Operation Corps, Dr. Dian Adrianto, MSI, and Mr. Iwan Yahya. And here are our appreciation sign for you. For the first session, we have Mr. Acep Purkon. And also we have Professor Nafarizal Nayan. And also to our moderator, Professor Budi Purnama. And the latest session, we have Lieutenant Colonel of the Indonesian Navy Operation Corps, Dr. Dian Adrianto, MSI. And also Mr. Iwan Yahya. And also to our moderator, Mr. Surya Kusuma, MSI. And ladies and gentlemen, we are now at the end of the plenary lecture, and the next agenda will be the parallel session, which begins at 1 p.m. We give many thanks to all of our incredible speakers for today's plenary session, and to all participants, you may leave this Zoom meeting and please be back at 1 p.m. See you and have a nice rest.